Okay, so let's work this problem. We want to know the displacement of the beam. We'll just do this one right here. We'll just do at D. So we've talked before that looking at the real load system, we need moment equations. So we'll have to write one moment from 0 to 6, even though the load's continuous with this applied concentrated load at 6 feet. We'd have to write one that's good from 0 to 6, and then a second equation that's good from 6 to 20. And the other thing we need to deal with is that at C, the moment of inertia of the beam changes. Since I only want to do D, then my virtual system, I'll wipe out all the loads and I'll put a vertical load, my virtual load of 1 here at D. So that I'll need a set of equations for that. So let's start this problem. So the first thing I need to do is I'll probably, let's see, what should I do? I think I'll avoid getting my reactions. So when I cut the structure, when I cut it somewhere here between 0 and 6, I will look at the right-hand side. You can do that, right? So this will be the real moment. And this first one will be somewhere between 0 and 6. So if I cut my free body diagram here, let's see, what do I get? Well, I know I'm measuring x in this direction. So what is the remaining length of this structure? Well, the total distance is 20, so this should be 20 minus x. I have my distributed load, which has a value of 1.2 kips per foot. And then I have my 6 kip force. And then internally, I have my moment. So I'm going to measure everything from that cut surface, the moment surface. So what is the distance from the 6 kip force to the cut? Anybody know? 6 minus x. So when x is 0, the distance is 6. As I move out to 6, the value gets run. So I'll just go ahead and write in that this is 6 minus x. I'll go ahead too and also find the concentrated equivalent of my distributed force. So what's the area under the curve is 1.2 times 20 minus x. And of course, then the distance is what? 20 minus x over 2. I kind of squished it in there. I'm sorry for that. Everybody see all the information? So now I just start summing my moments. So I'll come over here and I'll say, I'll sum the moments at this cut. And let's see what we've got. So I've got the internal moment here, m, which is negative using right-hand rule. In fact, all the moments of all my forces are going to be negative. So I'll do the first one. So it'll be minus the force, which is 1.2 times 20 minus x. That's the force. And then times the moment arm, which is 20 minus x divided by 2. Then the 6 kip force, minus 6 times its moment arm, which is 6 minus x. So when I solve for the moment, I get all this stuff. So it looks like it's going to be 0.6. I take the half out of there. 20 minus x squared minus 6 times 6 minus x. Does that work? Well, unfortunately, for this situation, the only place I could know the moment would be at the reaction A, and I didn't calculate that. But you can see that when I put x equal to 0, I get a relatively large, I left off my minus sign there, I get a relatively large negative moment. So I'm just going to have to hope that that's right. Don't have any way to check it, unless I go back and calculate the moment here. Let's see if I can do it in my head real quick. It should be 6 times 6, which is 36, and then 20 times this, which is 24, times 10, 240 plus 36, 276. So put in 0 here and see if you get 276 real quick. I hate to work this problem, start off wrong. There's 36, and there's 400 times 0.6. Hey, all right. So let's do the next one for our real moment, except this time we'll do it from 6 to 20. So we'll cut the structure now somewhere here, and I think it'll be easier again to work the free end, or the cantilever end. So I'll draw a spot for that. So again, we'll be coming out some distance x, and our length of the structure is 20 minus x, as before. We have our internal moment m, and we have, in this situation, only the distributed load with the same value, 1.2 kips per foot. So now I'll get the concentrated equivalent of that, which interestingly enough is the same as the first one. And of course then the distance to the centroid is also 20 minus x over 2. So I have everything I need for my moment equation there. So I'll sum the moments at the cut. And what do we have? Well, I've got my internal moment, which is negative, and then this force, which is also negative, 1.2, 20 minus x, then times its moment arm, which is 20 minus x over 2. So that's not hard to find, that the moment is going to be this again. So it looks like it's just interesting, it's the first part of this. It'll be minus 0.6 times 20 minus x squared. Now in this one we do have something that we can match, because in this second section we do know the moment at D. What's the moment at D? 0. So I put in x equal 20, you can see I get a moment at 0. And you could match these two equations at the point they share, which is 6, and you should see it works out. So if I put in 6, you'll notice the second term disappears, and then these terms are exactly the same. So the moments match. It seems like these are decent moments. Well, decent not is that they're, not their character being decent, it's just that they're correct. How about that? It's a better terminology. So let's now go and do the virtual forces. So now let's find the virtual moments. So what does the beam look like? Well, the geometry is the same. So there's our beam. Moment of inertia is still getting bigger, except now we want the vertical displacement at D, so we'll apply our 1 at that position. So again, this is 2I, and this is I. Those are not going to affect the moments, so we should be okay. So I can write one equation for this. So if I cut the beam anywhere I like, again, it's going to be easier to work the cantilever in than the end with the fixed connection. So I'll redraw that. Bless you. So there's my virtual load of 1. And again, we'll measure out to the cut surface. That's our X. And then the remaining piece for any value of X would be the total length 20 minus that. And then I have my internal moment. Now remember, for virtual moment we use the lowercase symbol for M. So then I'll sum my moments at this cut that I've created. Make sure they're in equilibrium. And what do I have? Well, I start off, I've got negative my virtual moment, and then I've got minus my unit virtual load times the moment arm, which is 20 minus X. So that's a pretty easy one to solve for. So my virtual moment, I'll go ahead and run the negative sign through there, so it looks like it's going to be X minus 20. Does that work? Let's see. The only thing we know now is there's no moment at the free end, so when X is equal to 20, it's 0. I'm just looking at this quickly and see that my reaction moment will be 1 times the distance, which is 20. So when I put in 0 here, I do get 20. So that seems to be a valid one. So far, so good? All right, so now let's do the integration part. So my displacement at D is defined as the integral over the length of the real moment, the virtual moment, divided by EI times dx. So for our case, what are we going to do? Well, if you slip back here for a second, you'll know that the real moment from 0 to 6 is this equation. So I'll match that with my virtual moment. So I will have a first integration from 0 to 6 of the real moment, which is minus 0.6, 20 minus x squared, minus 6 times 6 minus x. So there's my real moment. And then my virtual moment, x minus 20. So again, just to let you know, this is the little moment, virtual moment, and this is the real moment. Yep, sorry about that. And then we're going to divide that by normally EI. What time is it?
Yeah, 36.
All right, let me just finish this and we'll stop. So what's E and I going to be this time? Well, E is still E. But what's really I? 2I. So let's stop for a second and I'll start this up as a part 2.